this should be interesting because this will be the first time I try it in true high definition, which will mean that maybe the camera, maybe I can't tell what the camera resolution is. It says a USB capture HDMI. Let's see, what if I configure video, camera control? It does not show me what the resolution of the camera is. But I can compare this screen to the last screen in dynamics and see what it looks like. So I'll erase all that. All right, so I'll start in a second. You may be the only one that comes the whole semester. Yeah. Yeah. Well, you know, it's interesting. I mean, it puts I guess it puts a pressure on me, but it should, but it doesn't anymore. But it should, in which I'm supposed to be more entertaining, maybe? I don't know. Okay, so what's this mean? Backlight button. It just changes the light. Auto far near manual. Let's see what that does. Far. I don't see any difference. Okay, menu. Oh, exposure, color, noise reduction. What noise reduction does. Noise reduction level 3. It doesn't do anything. Okay, so forget that. Okay, again, menu. Communication setup, exposure, image. What does image do? Luminance, contrast, sharpness, gamma, style. I don't know what that means. Let's go to enter. It says go to home. Enter. Where's the enter key? Reset? No. Yeah, that's good enough. Here, let me see if it's online. That would be oh, there it is. Swipe to see all. Let's see. How do I look at this? What does that do? Quality. That's all I get. 720. I can't get. It reduces the quality for me. Why does it do that? All right, I might as well start. See, so this is chapter 2, as they say. And he calls that fluid statics, I think. And it basically revolves itself around this equation, which we'll find out later. This could be thought of as a subset of a non-moving Bernoulli's equation, and I'll show you how that happens. But essentially, all it is as you get in a pool of water and swim down, the pressure increases and so on and so forth. So now let's look. We did manometers, and we'll do more problems next time. Or not next time, next week we'll do, well, I'll try to get the camera set so that I can project off of my phone onto the board sections of the book, and then what I'll do is line up a problem and I can work it from there. May not be perfect, but I guess the other approach could be, since I'm logging in here, maybe I could project them off of the camera instead of off a phone. I could do off the computer, but I'll do that next time. So now if we move on, yeah, chapter 2. Oh, sorry, chapter 2. Yeah, chapter 1 was what he called, other books have different names for it, but it was fluid properties. It was essentially rho, the density, gamma, specific gravity, which some people list that as S, some people list it as SG, and then you got that, and then viscosity and all the things that go with viscosity, and that is the shear stress is equal to the strain rate. Did I talk about the traffic? You know, okay.
The analogy of we're all the same speed.
Yeah.
90 miles an hour.
Yeah, okay. I'm just, you know, I teach it so many times I forget what I said sometimes. And I know I've talked about it before, but I don't know if it was like yesterday or last year. So fluid properties mostly encompass this. Now there was a P equal rho RT and ideal gas and some gas things, but I kind of think that's covered in thermos. So I'll just say, okay, there's a similarity, and we just go on. But in this whole chapter is primarily focused on the implications of that, in that as you go down in some sort of liquid, the pressure increases because of all the stuff over your head, you know. You could look at it like, you know, if you take a submarine, I'll take it as a box, say. People don't make submarines as boxes, but if you took it as a box and you took it down under the water, you know, you would find you'd have a pretty large pressure here on the top. You'd have a slightly larger pressure on the bottom because it's slightly deeper. But then what you would have is this vector. These lengths would be the same, and these lengths would be the same. And what you would find is the pressure on the sides of the submarine, which people don't make submarines this way, by the way. So all of that hydrostatic pressure is just meant to try to collapse that box, which is why submarines are not made like a box. They're made like that. It's harder to crush that than it is this. So you don't want to make a box submarine. I guess if you're like playing around and that's all you've got, you can make a boat like that and float around in it. There's actually some competitions where they do that. Make cardboard boats, put them in lakes, and they paddle across, and whoever makes it wins the prize. So you got to soak your cardboard in something to keep the cardboard from getting wet. So in essence, the key is deeper you go, the more pressure you got. So now let's take a situation where you're trying to build a gate. So you have this gate, big piece of metal that you're going to hold this is a hinge, and you're trying to hold back some water. So here's your ground, and maybe it can leak out a little bit, like a trickle out, but you want it to hold it back. So you have water, so say at 62.4 pounds per cubic foot, and say this gate is perfectly square. Say it's, well, it doesn't have, it can be rectangle, it can be this wide and this tall, but let's say it's rectangular in the sense that a person back here who looks out here and sees it in their brain, they see this, and there's the hinge. So they're seeing this. They're seeing this is the part into the board we don't see. So let's say for the lack of or sake of argument, it's 1 foot. So it's 1 foot into the board, and say it's 10 feet out. In other words, 10 foot from like the water down to this part right here. So we know that the pressure varies as the depth. So as we go down, further we go down, the higher the pressure is. So if we want to plot gauge pressure, then what we would have is this linearly varying pressure, which I'm going to kind of erase this part, which basically starts at the top, increases, and looks like that. Now, if you stare at it long enough, or maybe you tilt your head, if you tilt your head, now I'm going to erase the guy over here. Say if he tilts his head, what you find out is here's the hinge. You have nothing more than a triangular load on like a beam. And this beam is 1 foot into the board, and it's 10 foot long, and suddenly you've moved from a fluids course into a statics course. And that's why they call this section fluid statics, because, you know, after you get past manometers, and when you get into gates, everything you see kind of looks like statics. So, and it is statics, nothing's moving, it's static, you know, that kind of stuff. So in essence, to keep this gate from swinging open, somebody has to go back here and like bury some big piece of concrete so that the thing is pushing against it. So this concrete is pushing against the bottom of the gate, and hopefully the hinge is holding it, so it's going to be holding it that way too. So what I really should do, and actually let me remove this and say the hinge could actually hold the weight of the gate up. So I'm going to put this right here as this being HX and HY, and say a reaction load. So now I'm going to put them over here, but when I start doing some of the moments and everything, I'm going to be referring back to here, but this is just to show you that it's the same thing. Let me erase this board 1 foot and say this is HX. It doesn't look like HX, but here's HY. Now here's what I'm saying. The gate may weigh a certain amount, but this is the weight of the gate because the gate, this is where it's actually oriented in space. So here's gravity. Gravity is making it come down. So if I sum my forces off of here, sum my forces in the y direction, actually I've got a minus weight plus the hinge y, and then I get a pretty boring thing that the hinge is holding the weight of the gate, and that's all it's doing. But the HX is where things get really interesting. So in it, let's go back and say, now I'm not going to worry about, because I solved that over here, I'm not going to worry about that right now in here. I'm just going to look at the X components. So I'm looking at the X components, and back when you were in statics, one of the things you did is you did this. Okay, let's see. Reaction and hinge in the X, and you replace this load with an equivalent load, and it was 1/3 over, and it's 10, so I'm going to say this is 10/3 from the heavy end, and 2/10 from the light end. And so there you sit, just like that. And now you can work off of that upper one. But to work off the upper one, you need the information in order to figure out what this load is. I call it L. I could call it something else. To do that, you got to come back into fluids. And into fluids, you realize, let's look at the pressure at this lower depth. The pressure at the lowest spot is equal to gamma of 62.4 times how deep did we go? Okay, let me move this back. Pressure at the lower spot is equal to 62.4. I'm borrowing this equation. This is the basis of everything. Times height, how far depth? I swam down 10 feet, or I get 624 pounds per square foot. That's at the bottom. And when you're in statics, you got this load generally as so many pounds per running foot. Running foot being running this way or running that way. That's what they mean by running foot. It's basically a foot in this direction. So, but you have the wrong thing here. So what you do is you multiply it times the depth. If this was 2 feet deep into the board, or if this gate were 2 foot wide, you multiply that times 2. I made it so it's 1 foot wide. And so that means the load here on this end is 624 pounds per running foot. Of course, on that end, it's nothing. On this end, it's 624. And it just collapses or goes all the way linearly down to nothing. So then you're back in statics. Now you want to find the area of this thing. And so your area, so what you're looking for, the area of that triangle, the area, which is the load that gets put up there, is 624 times 10, but it's not, half of it gets clipped off, so it gets like that. So I don't know what that is. So it should be easy to figure out, but my brain, after hours and hours of, oh, wait a minute, okay. After hours and hours of lecturing, I get tired. 3,120 pounds. Usually one of the things you'll find out is these static gate things will sometimes give you really large forces. Water is, you've got to figure out how to manage yourself through some of this. That's a lot of force, actually. So now, all you're doing is, I've got a statics problem. I go over here, sum the moment, say about the hinge. And it's equal to 0, and I got to choose a direction. So I'm going to choose that to be positive, and so that makes that 3120 times 2 times 10 over third. That's how far it gets moved over to there. That's, 1/3 from the heavy, 2/3 from the light end. Then I'm basically looking at the entire distance, just 10 times r. So the reaction load ends up having to be, I don't know if that makes sense, 3,120 10 over 3, and slipping the 10 under there again means, okay, I should know how to do that. 3 says 12 is 40. 1040. The reaction load is 1,000 pounds for a 10-foot gate. Check that just to make sure. Like I said, yeah, 1040. So you end up with that. So in essence, if you've got a perfectly square gate like that, I mean, that's what you get, you know. We'll do a couple like this, and then Monday we'll start doing curve gates. Wednesday we'll do weirdo-shaped gates, and that'll wrap up the gates. The curved gates are kind of interesting, but, you know, still. So does that all make sense? I mean, it's kind of a borrowing from statics there. So, okay, so let's do one that tilts out at an angle. And then, let's see. Let me just draw this up and see if, I mean, you never know. Sometimes the internet works. Sometimes it doesn't. It's just highly variable. Let's see. Here. I wish if you were on campus, it would just automatically take you into Blackboard. You're logging in twice, but I'm sure there's a reason to do that. There's a reason for everything, so. So maybe I'll start trying to do it that way. Let's see, there's the fluids. Okay, go to there. Go to, oh, it went straight into there. Let's see how this goes. Okay. Table of contents. He's got, yeah, he calls it fluid statics, pressure, absolute gauge. Okay, so, wow, he goes, okay. Okay, I'll come up with that equation next time. I might as well, let's see if I can project this. I might be able to. I don't know. Sometimes the pressure, I mean, the projector works. Sometimes it doesn't. Plane surface.
So that is for 1 by 10 foot gate.
Yeah, 1 foot wide.
1,000.
Yeah, 1,040. So it's 10 foot deep. The biggest problem is the depth. If it was shallower, like if you took that 10-foot gate and you turned it sideways and it's 1 foot deep, it wouldn't give you much.
But it would still technically hold the same amount of water.
Yeah. Yeah.
Like I said, about wider dams or not, deeper dams.
He's got this broken, I think he's got it broken in a good way. Actually, I think he's done a pretty good job of breaking it. Is the projector? Oh, it is going. Okay. So he goes into here. Well, maybe I can do this so I can project on here. I can't make the screen. It's hard to tell. Let me look at the stream and see what I see online. Here we go. Okay, I'm going to go all the way to the point where I'm live. Well, actually I can see that pretty well. Let me see. That looks okay. I think I could actually, in fact, visually here in the room, you know, you see this measurement of static pressure behind this. Well, I guess actually technically, if you turn it sideways and get rid of the chat thing, you can on the screen, you can see the writing better than you can here in the room. Let's see, why is there no? Yeah. Okay, so maybe I'll start doing that. Maybe I'll start doing it now. Here, let's see. What's his example 2.5? Yeah, I'm down into here, though. Okay, so here's what I'll do. I'll go ahead and go, since he has this part first, I'll do this part first, and then we'll pick up and do, hey, and that's kind of beneficial too, because actually I can use this as the edge of the board and get the camera to focus in on the edges, and then I'll know exactly where I can write at and not write at. And besides, I can't really write up here anyway, so I can clip that part off on the camera. And I'll lose a little bit down here, but that's okay. So this is what he's talking about. He's kind of talking about, I'm watching myself at the same time, although I'm delayed. He's talking about the fact, you know what? This is really interesting. If you look online, this looks better on the phone than it does on the board. And actually, I can only zoom in a little bit. So on the tilted gates, he's doing a special equation. And what he's doing is this is a focal point here where he's got a coordinate, although he does not line it up exactly. And it is supposed to be lined up from here down to the location of an area. And then what he's going to do, now what happens is, but there's no gate here, so it linearly varies from 0, and the gauge pressure goes up and continues to go up, but he has no gate there, so the gate is only after it gets down a certain amount. Now here's the funny thing. Examples of this might include something like this. So you have a gate, starts here, and then what you do is you put a hinge, and you have the water sitting up here. So technically, what you're doing is you're extending this line back up until there's some location, a special location, in which you measure Y from. And so that's why he's shown this little area as being just all underwater. But back here, there could be something like that. And usually there is. The water holds it back. But you're supposed to extend the water surface and the gate surface until they reach a coalescence right there. That's where the Y is from. That's why that shift in Y bothers me a little bit. It's okay. It's just I'm being very picky there. Then what he does, okay, so he gets down here. Well, I guess he does it there as well, but it's not as bad, but it is still annoying a little bit, and that is that this line should originate from where those two cross each other. Actually, you know, maybe it does because he's showing the angle, and you look at the thickness of the gate, and it does go back to about right there. So I was mean to him, but I don't know. That's picking hairs. But actually, where the gate surface crosses and where the water crosses, that's the point where Y comes from. And it's supposed to be the gate that's touching the water. So if the water's on this side, it's actually, I've even drawn it wrong. It is actually here. So I was being particular, but I guess I should keep my mouth shut and go with it. So it's where the water line or the gate line that touches the water goes through. It doesn't matter how thick this gate is. I mean, on this side, this gate can look like this. It doesn't matter. none of it's touching the water. So what touches the water is this surface right here, so it goes back to here. The thickness could play in a role in how heavy the gate is, but so then what he does is he goes through, he basically says, the first thing he says is just diet. Technically, other books might derive that, and the way it's derived is kind of interesting. Is if you, let's see if he shows, he does show. Let's go to the upper view. So let's look at a list of the things he derives that he shows, and then I'll show you where they come from. The resultant force is gamma H bar A, which he put the H bar before the A. Doesn't really matter, but H bar A. And then there's a delta, which will be I bar XX over Y bar area. And there's another term there, but we'll scroll down and find that. And I'll show you where both these come from. So he just says that. And then let's see if we can go down a little bit more. Oh, well, he does kind of, oh, well, wait a minute. No, he doesn't really. Oh, well, wait a minute. He does. So what he's doing, he does show it. He just enters the equation first. So what he does first is he says to you, what if I could get this thing off of here? Is there a way to get that off? You know, I guess it really doesn't matter. He starts with this concept that there is a little D area. It's a very strange diagram. But as you move this D area this way or this way, it basically doesn't increase its depth. So in his thing, he's got a basically, which I think he probably listed not as a delta, but as a D force is equal to area times a D pressure. Well, that's gamma times H, which he lists himself as H, and that's the pressure, and then you got a D area here. But his H, if you look at the triangle, now let's see, where did he measure theta from? It's kind of strange, but here's this triangle. It's in a funny perspective. So, sine of theta is equal to H over Y. So if you want H, you can take the Y and multiply times it. And so what you get is a delta. You get it, I mean, sorry, that's the gamma. That's the 62.4 pounds per cubic foot if it's water. If it's something else, it's not that. Now you've got Y, forgot, sine theta d area. Now, as you move around and change your Y, you don't change that. You don't change that. So what you get is gamma sine theta y d area. Now if you look at this real close, that's nothing more than y bar. And so then you got this concept, if that's nothing more than y bar, okay, hang on. If this is nothing more than y bar, then y bar sine, oops, too many S's, y bar sine theta gets you back h bar, which basically says F is equal to gamma h bar area, because this is y bar times area right there. So you end up getting this back. So in other words, if there's a gate, it sounds weird, but let's say you had a gate that was like the shape of my hand, and you found the centroid like this. You moved it up and down and around. The pressure on that gate from this side is nothing more than the depth to the point of that centroid. That's the actual force that's on that gate. So it matters where the centroid is located. Of course, when you move the centroid down, you move all the other points down as well. You don't split the gate apart. It stays the same shape. And so that's where this comes from. And he actually has this in there. If you go down and look at this, hopefully the equation, I may have to zoom back out. So there he is with that. And he starts with the force, is pressure D area, gamma H, Y sine theta. And that's the gamma. That's what I was talking about. That in the book, this is his gammas, but I keep writing them on the board like that. So that's what you see in the book. This is what I've been writing. To me, I have trouble with that because when I start doing that, to me, that's pretty close to the mu, the dynamic or kinematic viscosity. So I have trouble on the board distinguishing between that symbol and the kinematic viscosity for me writing on the board. So my gammas will be like that. His gammas will look like that. And I'm sorry about that, but then you roll on down. He integrates this. Oh, and now I got to zoom back out. How do I get rid of this thing on the left? I can't. It just gets stuck there. Okay, so there, and I can't move to the right. I just have to keep zooming back out. Okay, so there he is with that. So when he gets there, there's your Y bar. There's your sine. Oh, it selected the whole thing. Okay, go away. So you take your sine and Y bar, that gives you back H bar, and that gives you back the equation. If I click that, it makes it really big right there. I don't know that, does it do that with that? No, because this is actually, that's an actual equation. This is actually not an equation, that's an image. And that must be, what happened if I did that? Whoa, just in case you can't see it. Oh, and I can't get it to go any further. It goes to right there, that's it. So the resultant force on the gate or plate or whatever, okay, go away, go away. Specific weight of the liquid, the centroid, the depth to the centroid, and then the submerged area of the plate. Then he talks about the location, and when you do that, what you're generally doing, when you're trying to find the location of something, what you're trying to do is you're trying to take, like you did in statics, you took a triangular load, and the only way that the way you set these as equivalent, there are two things you have to make them to be equivalent. One is the sum of the forces in the y direction have to give you the same force. The second is the sum of the moments have to give you. So in other words, if you stare at this point, this will produce a moment this way. This has to produce the same moment. So to make this equivalent to that, you have to make the forces equivalent and the moments. So what is the moment here? It's just the distance out times the force. So you found the force from before. Now what you're trying to do is make the moment equivalent. So you sum the moments, you take the y location, that is that, I called it D, and you take the resultant force, which you had before, and now you integrate those, and this comes off of the diagram where you're moving the dP around. So you notice this looks incredibly a lot like the previous, except there's the moment arm in there. So if you look back at it, you'll see the integration where I did gamma, y, sine of theta, d area. That was where you were trying to find that. And this was actually the d force. But now what you're doing is you're going to sum all these little bitty forces up, times the moment arm to them, and it gives you an extra y. Now what you get on the left side is you get what's left over here, and what you'll see is these combine all together nicely in a second as soon as I roll down. To get you this, which looks funny at first until you see that, which is Okay, he's using the symbol. Where did it go? Oh, it's right here. He's using a little bit different symbol. He's calling it YP. I called it delta. I bar X, Y bar A. And so we'll need to define this a little bit better. And to make this all make sense, the best thing to do is we will, and I probably won't be able to get there today, but next time we'll do problems using both methods to show that they always come up to be the same. And then, let's see, there's nothing more below that. Those are only, oh, he sets it up like this. Now me, okay, so this is my delta. Okay, let's see. I'll show you how I'm relating differently than what he's doing. So he says I bar X, Y bar A. He says the Y to the centroid. Now what is my delta? And me, the way I look at it, if you have a gate that sits there, okay, and say the centroid is right here. So if some person is sitting down here, staring up at it, he might see a gate that looks like this, you know, and its centroid might be right here. Since the pressure on the surface looks more like this, what he calls the center of pressure is a little bit below it. Why? Because there's more force down here. Here, let me make that straight, because this is just to make it, we can go back and look at standard forms of it later. The fact of the matter is, there's more pressure at the bottom, meaning that this is where the resultant load is going to go. It's going to be a little bit below the centroid. And it turns out, how far below? That's what I like to say. How far below the centroid is that force? And that's where it is. His equation is basically this. The center of pressure and the centroid, you move those over, YP minus Y bar equals to I bar XX, and I always put an extra X, just because it's a tensor, really. And so this is, okay, so here's your Y bar, and, I'm sorry, there's a Y bar. Here's YP, and if you take, I'm sorry, YP, here, okay, that's not GP, that's YP. That one's slightly larger than that one, meaning the center of pressure is a little bit below it, and the distance it is this. So in essence, what I say is that's what I always think of. That's what I'm looking for. How far below that centroid of the object is the center of pressure. And that's the way I look at it. Less things to remember.
That's all in reference to that.
Yeah. The geometry.
Yeah, the geometry of it.
Yeah. So if you find the centroid, you already had to find the centroid. So to me, I'll just look below the centroid. And so that's just the way, that's my set. Okay. Oh, it keeps, okay, all right. So then what is this? Example 2.8. Okay. Oh, that's interesting. He has really nice graphics. I give him credit for that. It's like a box that was all screwed in. It has all this. And he's got his pressure, his resultant force. You know what? We'll come back in next time and do that. Maybe we'll do one more complicated. He's got a cylinder, not a cylinder, a circular window. He's got the force on it. You know what I'm going to do? Let's see. Can I get I'm going to go down to where problems. And maybe I'll go in here next time and start hammering away at some problems. Because what I'll do is look in the weekend and see how this is looking on the stream. It seems to be looking okay. It seems to, I mean, you can tell what's going on. The colors are slightly, I mean, the texture and everything is fine. Colors are slightly muted, but hey, We can just put these up there and work around them. So maybe I'll do that instead of putting the book on my phone and connecting. Yeah, because there's plenty of problems to work. I'll just start working some of those problems there. Nice colors, and I can actually shrink them down. And I can actually do this. Let's see. If I want to hide part of the screen to work, I could sort of put that in a way. Yeah, and that'll make this area of the screen so I can work on the board and take the picture out and do things like that. Then put MATLAB up there, I can do the whole thing. Yeah, there's plenty of problems there. That was, now what is that? Oh, that's a funny looking triangular gate that he's got there. Circular gate, nice graphics again. Curved gates, get into some curved gates there. And funny looking. There's a nice, beautiful curved gate right there. There is a curved gate which is bizarre looking. And that looks on the monitor screen. On this monitor, it doesn't look circular. On that monitor, it does look circular. So the question is, let me let this stream catch up, and does that look circular on the YouTube feed? Hang on. No, it's slightly shifted, but it's okay. You can tell that's kind of what's... So we'll do a bunch of these next time, and we'll use the equations, and then we'll go ahead and go into curved gates. There he's got a cable. Yeah, that'll be good. In the meantime, we'll just call it good for now. And then we'll all go home. Go away. Okay, go away. Go away. Go away. Go away. So I'll stop the stream. I don't need to save that.